Okay, hi. So second example is another small sample test. This means I'm assuming the outcomes are normally distributed. So, and I want to do a test that compares means from two different populations. So I have a table of only 5 each for men and women, their body temperatures. And we will assume we could call these like M1 to M5, so we assume, so here we assume, the assumption is MI, IID, normal, let's call it mu1, sigma squared. I'm going to assume they have the same variance, so that is one assumption that simplifies the calculations and is probably reasonable, at least in this case. Mu2, sigma squared. Okay. And in this case also they happen to be the same n, but in general you could have more of one population than the other and still do this test, okay? So this makes it a small sample test. So our test will be, we want to test to see if there's significant difference in the means. Now it appears the women in this experiment had higher body temps than the men, so we don't expect the men to have a higher mean, but we want to see if there's evidence that the women do. So the test that would make sense is want to test H0, that there's no difference, so we'll say this mu2 minus mu1 equals 0 versus HA mu2 minus mu1 greater than 0. And so, right, okay, very good. So, shouldn't be too much of a surprise. We can see that just like with our confidence intervals, we can use the sample means from each population and get a t distributed random variable. So, and I think this time too, we will show this as t distributed at the end of this example. So our test stat and our rejection region. So we want to reject, right, if we have reason to believe that if say the mean from this row here is significantly bigger than the mean from here. So our test stat is going to be, so our test stat will be a t variable again, but it's going to be, will be a transformation really a centering of, let's call it W bar minus M bar, okay? So if this is significantly big, then I will assume mu2 minus mu1 is greater than 0, okay? So it will be transformation of this, just because we want it, it makes it a little nicer. We'll have t equal W bar minus M bar, and now minus this mu2 minus mu1 under H0. This is actually 0, so I'll write that in just to remind us that that's that number. Okay, so I have the sample minus what it's expected, the difference of the sample means minus the expected value of the difference of the sample means under the null hypothesis. And now I want to divide by the studentized standard deviation. So this is going to be, we'll call this SP, the pooled standard deviation. And in here I have square root 1 over n1 plus 1 over n2. We'll show this at the end. Okay, so this is our test stat. And I have to tell you what SP is. It's the pooled standard deviation. I don't think I have room to write here. Maybe I do. So where SP is equal to n1 minus 1, s1 squared plus n2 minus 1, s2 squared all over n1 plus n2 minus 2, and this is to the half power. Okay? So you can see this looks like a weighted average of the two sample variances, and then I take the square root to get the square root of that, which is like a standard deviation. Okay. So test stat will be this, which is this, which under H0, mu2 minus mu1 equals 0, has the distribution t n1 plus n2 minus 2. We'll show this after we do the example. Okay? All right, so given this, then what should the rejection region be? So to make an alpha test, so let's do, for alpha equals, let's make it 0.01 this time. Test, we require RR. We still want it to be a right tail because I want to reject if this is big, and this is an estimator for this. So sorry if you didn't see that, this is an estimator for this one here. So we want RR to be the following: t greater than, and we just want this to be k, which will be qt 0.99, so the 99th quantile of the t distribution with 8 degrees of freedom. Okay, so this is k. Okay, all right. Okay, so let's do it quickly. I think I calculated most of this stuff. So if I look this up here, I did. So from R, we get, this is 2.896. Okay, and from the data, we find that T is equal to, let's see, I did this. I got the mean for the women temp is 98.08 minus mean for the men 97.48 divided by pooled variance 0.29 and the square root of 2/5. Each one's 5. Okay, and if I do this out, I get approximately 3.27. So we reject, right? So this is greater than k. So we reject H0 even at level alpha equal 0.01. If we want the p-value, let's see what the p-value would be. The p-value for the sample is, what should it be in R? How would you specify the p-value here? It's just, I have the, so here I'm here, right here's k, and here I'm over here at 3.27. I know it's less than 0.01, right? Because all of this is 0.01. So the question is, how much is to the right of 3.27? So this is this is the p-val, right? Okay, so the p-value is simply using r. It's just 1 minus pt, 3.278, and we get nothing too small, but 0.0057. So it certainly passes the alpha equals 0.01 test. So we conclude there is evidence at level alpha equals 0.01 to suggest that women have higher body temp. Okay, well, you might say, is this normal assumption reasonable? You can look at this two ways. Sometimes it is actually reasonable. There are certain cases where you can actually prove that it is normal if you have independence. The measurements are normal. Often, too, there's the argument that due to many random factors, natural measurements tend to be normal. So those are good reasons. And even if you don't know and you're skeptical of it, you just say you're making that approximation, and you go from there. You have to make some assumptions. One thing, though, there was no stage in either of these examples where we had to go and estimate sigma squared, right? Everything came from the data. So using the normal assumption, if that's fair, sometimes it is, sometimes it isn't. There are ways too to see if it looks normal, if it looks normal. So that's the only real assumption here, and it may be more valid sometimes than others, but that's it. Okay, so all I want to do now is just show that expression over here actually does have the t-distribution. We'll do it in the next lecture. Okay, so we will show this is actually t-distributed.